Hello and welcome. In this video, we're going to look at how to apply the voltage divider rule. The voltage divider rule uses our ratio equation for resistance, and we can remember it by saying want over have, specifically the resistance that we want to know the voltage drop across, VR1 here, and so we would put R1 on top as our want equation, and then on bottom would be our total resistance, and that's going to be what we have in the circuit. We can say that VR1 can be broken down using Ohm's law. Voltage is equal to current times resistance. So we can say that our IT, since this is a series circuit, there's only one current, it has to be IT. And the resistance R1, specifically, since we're looking for the voltage drop across R1. Right, multiplying those together would give us the voltage drop, but we don't know IT. So we want to break IT out of this equation also, and we can say that the current, in terms of Ohm's law, would be voltage divided by resistance. Specifically, total current needs voltage source or total voltage divided by the total resistance RT, right? Those two totals will get us our total current out. And so when we plug that back together, we can say that our voltage source divided by our RT multiplied by R1. Right? And these two can be rearranged here so that we can visualize our resistance ratio. We can put R1 on top and RT on bottom and multiply that by our voltage source. Kind of like we did with our percentage, but now instead of multiplying by 100, we're multiplying by 5 volts, and that's going to give us the voltage difference, the distribution of our voltage. That's what we see over here. This is our series circuit. Our 100 ohms is in series with our other 100 ohms down here, and that allows us to get our total resistance of 200. So if we place that into our want over have equation, we see that we want VR1. So we'll put R1 on top, 100. We'll put our total resistance on bottom as what we have, that's 200. Then we multiply by our 5 volt source. And that gets us 1/2 of 5 volts. And that's equal to 2.5 volts. And that's exactly what we measure on our XMM1 here. We should see the same exact voltage drop across the other one because we know that we start out with 5 volts. KVL says that if we subtract what we lost, 2.5 volts, we'll end up with what we have left over in the circuit, 2.5 volts. So VR2 should also equal 2.5 volts. Let's do one more here. This circuit has a different distribution. We have a same series circuit here where we have the 50 ohms and the 150 ohms in series with each other. So we'll add them together and that's going to give us our 200 ohms. We also expect that the smaller resistor is going to have less voltage drop than the larger resistor. So when we plug this into our equation, we can say what we want is VR1. So we'll put R1 on top, that's our 50 ohm. And what we have is the total resistance, still 200, so we'll put that on bottom there. And then we multiply by our voltage source of 5 volts. And that's going to give us our ratio of 1/4 of 5 volts. And that calculates out to 1.25 volts. We can do the same thing for our other resistor here. We can say that what if we actually wanted VR2? Right? VR2 is equal to 150, that's our VR2 value, divided by our total resistance of 200, that hasn't changed. We can multiply that by 5 volts, and we should output this to 3/4 of 5 volts, which is 3.75 volts. And that's what we expect for VR2. All right, let us know if you have any questions.